Hi everyone, I'm very excited to be here. My name is Supriya Rao and I'm an engineering manager at Meta working on PyTorch. Today I'm going to be talking a lot about PyTorch, specifically the new developments that we've had in the most recent release, which is PyTorch 2.1. So let's start. This is a little bit of the agenda that I'll be covering in the talk today. I'll first go over some background about PyTorch and some metrics associated with it. And then I'll be covering some of the new recent features that we've released. In the next part of the talk, I'll be talking about how to accelerate generative AI models using native PyTorch code. And finally, I'll be going over some model results on some of the generative AI models that we've benchmarked on. So let's get started. So PyTorch started about 7 years ago with a goal of powering researchers. Today, it's one of the leading AI frameworks powering diverse use cases, from self-driving cars to probably the AI robot that's running in your living room. It's open source, community-based deep learning platform. And if you haven't, you should definitely check it out today. And yes, we do welcome contributions from external people as well. So as I mentioned, PyTorch has grown a lot over the past 7 years. Here are some metrics or numbers that speak for the growth of PyTorch. In the chart on the left, you can see the growth in researcher usage over the past years. Currently, around 7,000 GitHub repos using PyTorch are associated with AI research papers this year. In addition, 60% of AI research implementations also choose PyTorch. In the graph on the right, you can look at the open source adoption, which is the number of distinct repos that are currently using PyTorch on GitHub. As you can see, there are over 600,000 repos that are using PyTorch today on GitHub. And we've also seen over a 20% year-over-year growth in the new repos using PyTorch. Let's look a little bit at the industry usage. PyTorch has also made a great impact on the tech industry. Data from LinkedIn suggests that over 65,000 LinkedIn professionals have PyTorch listed on their profile. There are also 3,000 jobs associated with PyTorch, and we've seen over 50% increase in PyTorch professionals this year. So with that, I want to talk a little bit about the last PyTorch release, which was PyTorch 2.0, which was released earlier this year. And it saw over 20 million downloads across different platforms. So it was a pretty significant release for us. It also added a bunch of new features, most notable of which is Torch Compile, which significantly sped up training and inference of a large variety of models. If you haven't, you should definitely go and check out Torch Compile, as a lot of external people are using it today. Flash forward to the next release, which is PyTorch 2.1, which is also what this talk is mostly going to be about. PyTorch 2.1 was released in October this year, on October 4th to be specific. And we also presented this at the PyTorch conference on October 17th. Going back to numbers, we saw close to 7,000 commits and 784 contributors that contributed since the 2.0 release. So thanks to all our contributors who are making PyTorch as great as it is today. So I now want to dive into some of the new features that we've added in 2.1. Starting with Torch Compile improvements. So as I mentioned, Torch Compile was a pretty significant feature for us that we added in 2.0. And we've been trying to continuously make improvements to it over the past few months. So the first one I want to talk about is automatic dynamic shape support. So for some background, deep learning compilers commonly only work for static shapes. That is to say, they produce compile programs which work for a single specific configuration of input shapes, and you need to recompile them if any input shape changes. With dynamic shape support, it allows Torch Compile to generate a single kernel that can work for many sizes at only a modest cost to efficiency. Dynamic shapes has been greatly stabilized in PyTorch 2.1, and it is now automatically enabled if Torch compile notices a recompilation due to varying input shapes. The next feature I want to cover is the support to compile NumPy operations. So PyTorch now provides support to it now understands the NumPy operations and it translates them into PyTorch equivalent operations. By doing this, users can now accelerate their NumPy programs using GPU CUDA kernels because this integration essentially operates in a device agnostic manner. The next feature is the composition of torch compile and autograd.function. Torch compile can now trace and populate the backward function of various user-defined autograd functions, which unlock training optimizations for models that make heavier use of extension mechanisms like autograd.function. The next thing I want to talk about is torch.export. Torch.export provides a sound tracing mechanism to capture a full graph from a PyTorch program based on new technologies provided by PyTorch 2.0. This can be run on different environments, which are also Python-less. In terms of numbers, using torch.export, we can capture a higher percentage of models compared to torch.fx symbolic trace, which was the previous version of graph capture that we had. And we've seen over 88% pass rate on 14,000 GitHub models that we've crawled and tried to run torch export on. One advantage of running torch export is that you get a graph, and so users can run custom graph transformations on this graph. And one of the transformations that they can run is, for example, quantization, which I'll talk about later as well. Another advantage of the export IR is that it can be serialized, saved, and transferred and loaded back for execution with or without Python. So it can be used for running programs on different backends, including edge devices or even DSP backends. So here's a small code snippet which outlines how to use torch.export. So torch.export extracts single graph representations by tracing the target function, given some example inputs. So in this case, if you look at the highlighted text, you're calling the model with sample inputs, and you generate an exported program by calling export. The next feature I want to talk about is torch export based quantization. So for some context, quantization refers to techniques for performing computations and storing tensors at lower bit widths than floating point precision, like int 8. So with torch export, we now added support for post-training quantization and quantization-aware training on models that are exported via this API. We also added a backend specific quantizer object, and this quantizer object allows the backend developers to specify how they want the model to be run on their backend, and the users can interact with this if they want to quantize PyTorch models to run on specific backends. And this API is programmable, so both the backend developers and users can modify it in order to get that level of control on how they want to optimize the model. We also have an option to specify the quantized computation using integer arithmetic in PyTorch. The place where this is useful is if you want to gain higher numerical precision and be able to debug your quantized model on the server itself before deploying it on various devices like edge devices or mobile phones or DSPs. So here's a code snippet on how you can use this new quantization API. So you have a module, a class M here, and you first have to capture them, like do export. So that step is called program capture. And the next step is quantization. So here you have a backend specific quantizer. So here we are calling an XNNPack quantizer, which is written for users to run their models on XNNPack backend to run on various ARM CPU devices. and you call the prepare function with this particular quantizer. And what this does is it inserts various operators into your graph to specify which layers you want to quantize and what precision you want to quantize them to. And then you perform either the calibration for post-training quantization or training step for quantization aware training. And the last step, you convert the model to the final quantized model by calling the convert PT2E step. Okay, so the next one I want to talk about is 2 out of 4 semi-structure sparsity. So torch.sparse now supports creating and accelerating compute over semi-structured sparse tensors. Semi-structured sparsity is a sparse data layout that was first introduced in NVIDIA's Ampere architecture. So what it essentially means is 2 out of every 4 values of the weight tensor have to be set to 0. In PyTorch, we've added support for creating such a tensor using a single one-line API. We also support accelerated inference via both QSparse-LT and Cutlass kernels, which enable you to run faster sparse matmults. QSparse-LT is a library provided by NVIDIA, and we've also included that in the nightly versions of PyTorch. So by applying 2-4 sparsity, you can achieve a compression ratio of 56% if you're using float 16 precision, and you can achieve a compression ratio of 62.5% if you're using int8. So here's a code example of how you would use this. So as I said, it's a single line API. So if you have the weight in the particular 2-4 sparse format, which is specified by calling this mask operation. So this mask operation is essentially zeroing out 2 out of every 4 elements here just for demo purposes. And you can then update the parameter of any of your linear layer with this particular weights by calling the toSparse semi-structured API. And then when you run your linear operator, you can take advantage of the accelerated kernels during inference. So we talked a little bit about the new features that we've added in PyTorch 2.1. Now I want to shift gears a little bit and talk about generative AI models and how you can accelerate them using PyTorch. So as you all know, the space of generative AI is rapidly evolving. As you can see, many innovative models have released in the last couple of years, each of them pushing the state of the art of what's possible in this domain. As with any new model released, the community wants to have a way to be able to run it efficiently on different hardware. The generative AI landscape is no different. From llama.cpp to other frameworks like Mosaic ML or XLlama, we have many different options of frameworks that have been built to run these models faster during inference. But can we do this with native PyTorch? That's a question we're trying to answer here without having users to rely on multiple other frameworks, but stay within the PyTorch ecosystem. So I want to talk through a few different techniques that we recommend that can be applied to generative AI models, and then we can go over the results that we saw on models using these. So the first one I want to talk about is SDPA, which is short for scale dot product attention. So at the heart of every generative AI model lies the transformer-based architecture. And in PyTorch, we include a high-performance implementation of the transformer API, which is using a custom kernel architecture for the scale dot product attention. So we have multiple different kernels that we support for SDPA, and each of this has custom kernel selection logic, which will pick the highest performance kernel for a given model and hardware type. So here I've listed the 2 options that we have. The first is the flash attention kernel, which is the kernel that was associated with the original flash attention paper. And then we also included the XFormer's memory efficient attention kernel, which is another variation of this kernel, which may work for certain different hardware types. There was also a recent version of flash attention that was released called Flash Attention V2. And we have also included that in PyTorch 2.1. And this is expected to be 2 times faster than the previous SDPA implementation of flash attention. And this is all available to you out of the box if you use PyTorch 2.1 with Torch compile and use the transformer API. So this is an example usage of the operator. So it's a simple single A10. It's a functional operator. It's called scale dot product attention, and you can call it with the query key value inputs. And under the hood, it will make sure to get the fastest kernel available to accelerate this. The next feature I want to mention is called nested tensors. So nested tensors are slightly different than regular tensors. In a regular tensor, each dimension has a size associated with it. Nested tensors are similar in some ways to regular tensors, except for their shape, where not all dimensions have regular sizes. Some of them are jagged. So it is useful for representing data that might be ragged. And in terms of practicality, it is a natural solution for representing sequential data within domains like in NLP, where you have sentences and sentences can have variable length. So a batch of sentences forms a nested tensor. Or in computer vision, where you have images and images can have variable shapes. So a batch of images forms a nested tensor. And we've observed that just by batching the inputs into a nested tensor format, we can gain significant speed up on the model inference. So for example, for the segment anything model, if you run the image inputs serially, the inference time is about 213 milliseconds, and that drops to 76.5 milliseconds when we batch the image inputs using nested tensors. So that's over 2.8x speed up in eager mode that you can see. So this is an example usage of how nested tensors look. So here you have two tensors, A and B, both with different sizes. And when you call the nested tensor API with A and B, it creates this new nested tensor class, which contains both the individual tensors inside it. Okay, so the next technique I want to talk about is GPU quantization. So we touched a little bit on quantization in the previous section. Look, essentially, quantization trades off numerical precision for reduced model size and increased execution speed. There are also other benefits of using int8 math over FP32, which is that you can reduce the model size by 4 times on disk. The matrix multiplication operation itself requires less computation because you're storing less data. And there are theoretical speedups of up to 16x by running the math in int8 instead of FP32. So there are different techniques that you can use to do GPU quantization. There's dynamic int8 quantization, which is dynamically quantizing the activation tensors while also quantizing the weights. There's static int8 quantization, which computes the quantization parameters for the activation tensors and also quantizes the weights. And then there is weight-only quantization, which, as the name suggests, only quantizes the weights and leaves the activations in full precision. So we ran GPU quantization on a couple of models like segment anything and llama 2. And with int8 dynamic quant, we see close to 9% speed up on segment anything. And on the llama 2 with int8 weight only quant, we see close to 47% speed up. So the API for this is currently experimental in PyTorch, but you can definitely try it out if you're interested. So the user would call a single line API like apply dynamic quant, as you can see below here. And what this does is it does a module swap of the nn.linear layer with a custom linear layer that can do dynamic quantization. And the class for the custom dynamically quantized linear layer is also mentioned here, which has a forward function which calls the specific int8 dynamically quantized kernel that gets run during inference. Okay, so the next one I want to talk about is 2 out of 4 sparsity. Um, Going along the line of improving the speed of matrix multiplication, quantization is one technique. Two-force sparsity is another way to get that accelerated compute. Um, and it is also possible to fine-tune the models to have negligible accuracy drop with 2/4 sparsity. And the way we can do it in PyTorch is you compose it with the torch.ao.pruning APIs to use different algorithms to prune weights. And then finally call the semi-structured sparse APIs to convert those prune weights for a particular layer and run the accelerated kernels during inference. We can also compose 2/4 sparsity with int8 quantization, and that can give us up to 62.5 compression ratio for weights and up to 4x theoretical speedup compared to dense FP16. So this is an example of how you can apply sparsity on your model. So the first step would be to actually convert the weights to the 2/4 sparse format. And you can use some helper functions that we have to do that. In this example, there is a weight norm sparsifier, which uses the norm function to figure out which values to zero in the weight. And once the weights are updated, you then call the toSparse semi-structured function with an updated weight and pass it to the linear layer weights. And in this example, it's all one-shot post-training, but you can also call these APIs during training if you want to further improve the accuracy of the model. The last technique I want to go over is 4-bit GPTQ. So weight-only quantization is a technique to accelerate compute when you're memory bandwidth bound, and 4 bits enables a way to store the weights in 4 bits, but that comes with an associated accuracy impact. And GPTQ is a weight quantization technique that helps to alleviate that impact to accuracy. So we leveraged the torch.export flow and prototyped an easy to use GPTQ implementation. And we ran this on GPU, but we did use a custom 4-bit group quantized matmul in CUDA. So this again is an experimental API, but this is how we implemented it. We have a GPTQ handler that calls the model and it stores all the state associated with quantization. And then the convert for runtime actually does the quantization function. And you can also load the quantized state dict into the quantized model at a later point. So you can perform the quantization ahead of time and then directly load a quantized state dict into the model for runtime. So I now want to go over some of the results that we got from applying these techniques. I'll go over two model results here. The first is segment anything. So as you can see on the left side, we have the performance improvement or the improvement in images per second after applying the different techniques on the segment anything model. All these experiments were run on an A100 80 gig GPU. You can see overall we have a 1.7x speed up over the FP16 eager baseline. And the two techniques like dynamic quant and sparsity have some impact to accuracy, but we observed no accuracy impact with int8 quantization. And we did see some accuracy impact with 2/4 sparsity because we were just doing it one shot and not really pruning during training. On the right-hand side, you can see the graph, which shows the reduction in the peak memory utilization during runtime. And we see over a 2x reduction in runtime memory utilization from applying all these different techniques over the FP16 eager baseline. I want to next touch upon the Llama 2 inference results. So here I'm mainly highlighting three main techniques that we applied on Llama 2. The first is torch.compile, and then we applied int8 weight only quantization, and then applied 4 bits GPTQ. So overall with 4 bits, we see over 7.5x speed up over the FP or the float 16 eager baseline. And we also have minimal accuracy impact at 8-bit quantization. And the accuracy impact at 4 bits is significantly mitigated using GPTQ. As you can see, it is pretty close to the even the float 16 accuracy for different cases that we analyzed. We also added speculative decoding, which is another technique that we included, which was a paper that we included in the Llama 2 results. And here with int4 quantization plus speculative decoding, we can go up to 244 tokens per second on Llama 2, 7 billion. And on the 70 billion model, it is not possible to run this model on an A100 80 gig without quantization. And we are able to run it with quantization and speculative decoding and tensor parallelism at close to 80 tokens per second. So the code for these two models are available today for you to try out. So for segment anything, the code is already available in PyTorch labs. And we are close to releasing the code for the Llama 2 as well. So hopefully you can check that out shortly, and please tag us on any issues or feature improvements that you'd like to see. With that, I would like to thank you all for listening to this presentation. And in case you have any questions, I'll be available on the channel to answer them.